Kia ora. In this video we're going to look at a few integration examples. We're not going to go for the seriously hard things, but we're going to do an example of each of a few different techniques that you're going to come across when you're solving integration problems. So we're going to start with one using the Fundamental Theorem of Calculus, which is the one that relates differentiation and integration together. So the type of problem that we're going to look at first is one like this one here, where we've been asked to differentiate a function g of x which is given as an integral. Now this is an integral that's got the variable x in the limits. That's our clue to use fundamental theorem. I'll show you why in a second. And we'll make it u cubed over 1 plus u squared du. Okay, so first off, your clue here is that we have our variable x inside one of the limits of integration. That suggests that this theorem here is going to come into play. This is the one that basically says if you differentiate an integral that's got x in it, then what you basically get is the function inside the integral back again, so long as it's in this form. So our function is not quite in that form because we've got our x in the bottom limit, whereas to use this theorem, you've got to have x up here. So the first thing we're going to do is we're going to take advantage of the fact that you can just reverse the integration limits by putting a negative sign out the front. So same thing. So now we are closer, but to use this theorem, it has to say x up the top, not 1 minus 3x. So what we're going to do is we're going to do a little substitution. We're going to say, let some other variable, let's call it t, equal 1 minus 3x, and then we're going to put that in there. So now we're going to have g of x is the integral from 1 to t of u cubed over 1 plus u squared du. Okay, now we've sort of solved one problem, but we've created another one. We've got rid of the 1 minus 3x and turned it into a single letter, t. But now our integral is in terms of this t instead of x. Don't forget this variable u is just a dummy. It comes out when it gets integrated. But the thing we can do is we can differentiate that right-hand side with respect to t, according to our formula, because t is the thing that's up here. So we can differentiate it with respect to x here, with t here, not x. So we're going to have to use a bit of chain rule to make this one actually work out. So I'm going to differentiate both sides with respect to t, because that's the thing I'm allowed to do. And I'm going to have put the negative sign at the front, 1 to t, u cubed over 1 plus u squared du. Now the right-hand side integral here, that is in the right format for the fundamental theorem. Okay, it's the integral from a constant a to the variable, so constant 1 to the variable of something or other in terms of a dummy variable. Ours is u, du, so t dt in the statement. And so we can undo that derivative integral just by taking what's inside. So that will be basically the function inside, but expressed in terms of the variable t. So that will be negative t cubed over 1 plus t squared. That's nice. But on the left-hand side, I am finding the derivative with respect to t of g of x, whereas the thing I actually want is dg dx. Okay, so this, if we just write this out using the chain rule, so dg, so the derivative with respect to t of this is going to be dg by dx, dx by dt according to the chain rule. The derivative we actually want is dg dx because our function started off in terms of x. So we're just going to need to throw in whatever dx by dt is to make that correct. Okay, so we've got x. Now just look at this bit here. This means that x is equal to t minus 1, or so 1 minus t, all divided by 3. So dx by dt is therefore equal to negative 1/3. So we'll put that in, and we'll get dg by dx times negative 1 over 3 equals, now we'll also put in all of the t's back into x's again, so it's going to be negative 1 minus 3x cubed over 1 plus 1 minus 3x squared. And so last but not least, we'll just multiply through by that by 3, negative 3, sorry, on both sides to give us dg by dx is equal to 3, 1 minus 3x cubed, all over 1 plus 1 minus 3x squared, and there we go. Okay, so we had to do a little bit of work to get this into the right form to use the fundamental theorem. The two things we did is we flipped the integral upside down, we changed its limits, we reversed its limits here by just making it negative, and then we substituted to make it to have a different variable so that we could have a single variable at the top. And we dealt with changing back into x again at the end by using the chain rule. Alright, next thing we're going to do is we're going to do an indefinite integration example, just to make sure we're comfortable with those. So let's say we want to find the indefinite integral, so it's got no limits, of the hyperbolic cosine, cosh, of t by dt. And in case we've forgotten what that is, it's just defined to be e to the t plus e to the negative t over 2. And we'll deal with that definition rather than just remembering. So maybe if you watch one of the previous videos, you might remember that hyperbolic sine, or sinh, differentiates to cosh and vice versa. So we could just write down that it was sinh, but we'll actually do the integral in terms of the exponentials. So that equals the indefinite integral of e to the t. I'll put the half out the front, e to the t plus e to the negative t dt. And all we've got to do is just do those pieces separately. So it's going to be 1/2 e to the t integrates to e to the t, e to the negative t integrates to negative e to the negative t. And you can always test that you got your signs and things and constants right by differentiating again and making sure you get back to where you started. Okay, and that just happens to be sinh, or hyperbolic sine of t. Now I'm missing something. When we do an indefinite integral, what we've found here is a single antiderivative. It's one function that will differentiate to give us cosh. Differentiate to give us cosh. So to express all of the possible ones, we just need to make sure we put on a constant of integration. So now we have a family of antiderivatives. Any value of c will give us a valid function that differentiates to give us cosh. Okay, so moving on. That's a relatively straightforward one. Now we're going to do a quick substitution problem. So a very common integration technique, and probably the one you'll end up using the most, is substitution. So we'll combine substitution with a definite integral, and we want to do e to the 1 over x squared dx. Okay, now substitution is basically something that you're trying to spot most of the time when you do a problem like this one. If we just express it in terms of, if you've got a sort of in general, you've got something, some function of some other function. So you kind of got two things stacked inside each other, and it happens to be multiplied by the derivative of that inside function. And that's when you can spot something like this, that means you can use the substitution u equals g of x to sort this thing out. So what you're looking for is a function. This is what the g is being here. And it could be buried inside a whole lot of other operations. But what you want to see is its derivative multiplied outside of everything. And if you do that, then your integral is going to simplify if you sort of go through the steps of the substitution. So what we have here is, well, my function, let's have a think about what that function could be. So we've got e to the 1 over x, so it's like we're taking 1 over x as our function, and then we're doing e to that. So our inside thing is 1 over x. So if I just think about 1 over x just for a second, maybe that will work. What's the derivative of 1 over x? Well, it's negative 1 over x squared, right? So d dx of 1 over x is negative 1 over x squared. And you can see that we have 1 over x squared multiplying this overall function, or if you like, it's a negative sign missing, but we don't worry about any constants. constant factors that might be multiplying it. We're just looking for sort of the mathematical bulk of it, the 1 over x squared piece being there. So we could rewrite this, just to be a little tidier, as the integral from 1 to 2 of 1 over x squared times e to the 1 over x dx. And again, I don't care that I don't have the negative sign or any other constant going on, it's still going to be fine. So this suggests that we can use this substitution here, so I'm going to do that. So I'll say let u equal 1 over x. And the other thing we have to do when we substitute in, we don't just replace the 1 over x with the u. We have to consider a few things. We have to replace the dx with the du with an appropriate factor on it, and we also need to make sure we deal with the limits of integration, because remember these are x's at the moment. So first thing we need to do is we need to do du by dx. So we need to differentiate that, gives us negative 1 over x squared. And so you can think of this as saying du, it's not quite mathematically the right thing to do, but it sort of symbolically it works, so you can do this. That means that du is negative 1 over x squared dx. And in fact, we could solve this for dx, which would say that dx is equal to negative x squared du. So what we're going to do is we're going to take that dx and we're going to stick it straight into there. And you can see that x squared is going to cancel off the x squared that's at the front of our fraction. Now the other thing we need to note is what to do with the limits. So when x equals 1, you can see that u is equal to 1 over 1, which is just 1 as well. And when x equals 2, u is equal to 1 over 2. So putting all that in, we get integral becomes the integral from u equals 1 to u equals 1/2. Now it's a bit weird to have the half above the 1, and we can reverse that in a minute if we want to. It's going to be 1 over x squared e to the 1 over x. Now 1 over x was just our u, and then dx was going to be x squared times du. Sorry, negative x squared times du. Now here's where, if everything has gone right, then what should happen at this point is that the x squared should cancel off, and we should be left with an integral that's purely in terms of u. So that equals the integral from 1 to 1/2 of negative e to the u. The x squareds cancel, du. Now, you can leave it like this, but to me it just looks a bit weird having a smaller number on top, so we can just reverse the limits of integration by multiplying, by basically making it negative of what it is at the moment. So it is also equal to the integral from 1/2 to 1 of e to the u du. Okay, so finally we can do the integration. So that will equal, oh, e to the u just integrates to e to the u. That's nice. And we evaluate it between u equals 1/2 and 1. So we don't need to go and switch back to x. We can just basically use these u values and it will be fine. For some problems, it might be more convenient to switch back to your original variable, especially if you've got some trig or something involved. But either way is going to give you the right answer. So that was going to be e to the 1 minus e to the 1/2, and there's not a whole lot more we can do with that. All right, we are going to do one more quick substitution problem that's not quite of this form, just to show you that it can sometimes be a useful tactic even when you don't get this derivative cancellation trick. So for our last example, we'll just do another substitution where we have the integral of x squared root 1 plus x dx. Now for me it's maybe not so obvious what you should do here, because you kind of, often your eye is drawn to the thing that's inside another thing, like the 1 plus x is inside the square root. But the derivative of 1 plus x is just 1, and so it's not like I have 1 multiplying the outside of my thing here, which will just cancel off like our last example. But let's see what happens if we just make that substitution anyway. So we'll say let u equals 1 plus x, and then we'll get du is equal to dx. I should do it in 2 steps, shouldn't I? Du by dx equals 1, which means that du equals dx. That's nice. Don't have to worry about limits because this is an indefinite integral. So let's just see what happens. So our integral becomes the integral, now x squared, okay, we'll leave that for now, x squared root u du. Now this time I've got some x's left over, so why don't we instead work out what x is from our substitution. So x is u minus 1, and we'll put that in as well. So that equals the integral of u minus 1 squared root u du. Okay, now I don't know if maybe it's not obvious how that's helped, but let's just expand this all out and see if we can sort of write this in a slightly happier form. So that's going to be integral of u squared minus 2u plus 1 all times root u du. Now remember, root u is just the same as u to the half. So I can just combine all these into individual powers of u. So that's actually equal to u to the, so 2 plus a half. So it's going to be u to the 5 over 2 here. Because u squared times u to the half is u to the 2 plus a half, which is 2.5, which is 5 over 2. Similarly, minus 2u to the power of 3 over 2 plus u to the half du. And now these are all things that we can integrate, okay, because we know how to integrate powers. So that will be, what do? Well, we increase the power by 1 and then we divide by it. So if, for example, if we've got integral of x squared dx, we increase the power by 1 and we divide by that new power. So this is going to be u to the 7 over 2, and we divide by it, so there'll be a 2/7 out the front, minus u to the 5 over 2, and we divide by it, which is going to be multiplying by 2/5, so it's going to be 4 over 5, incorporating the 2 that was there before, and then plus u to the 3 over 2, divide by that is 2/3. And then because it's an indefinite integral, we add on the plus c. Okay, that's enough integration for today. We'll see you next time. Ka kite anō.